Good morning, ladies and gentlemen. Thank you all so much for joining us today on our webinar, Safe Return to Port, Principles and Impact on Design. So I will start with giving you a quick idea of how the webinar will progress. We will start with a short introduction to our panelists today and our business, and then I will pass on to Alistair for a presentation on the SRTP regulation, which will take about 25 minutes. After that, Trifona will take us through a practical example of modifications to a freshwater cooling system to make it compliant with the regulations in our software tool Sistema. This will be about 20 minutes. After that, we will do about 10 minutes of question and answer. Regarding the question and answer session, please use the Q&A functionality in the bottom right-hand corner of your screen. If you go to full screen, which I strongly suggest so that you can see the Sistema product well, then you can get pop-up windows for your question and answer and chat windows. Please ask all questions to all panelists, and we will either respond immediately in text, and that will go to everybody, so it will be public. The question and the answer will be public. However, we are limited to 256 characters, so we can't make replies in text. Otherwise, we will also keep some questions and for the Q&A session and answer them verbally at that point. Phil will now share a link for everybody in the audience. This is a link if you have any issues, any technical issues with WebEx. So for the panelists today, myself, Vic, I've worked in the maritime software and consultancy business for about 20 years. Most of my time has been spent developing a stability and naval architecture tool. I joined Brookes Bell a couple of years ago and focusing on taking some of our great tools to market. Alistair, also known as Ali, has been with Brookes Bell business for about 12 years. He joined Brookes Bell as a naval architect, but quickly moved to developing our internal software tools. And he is now a full-time software developer, and he is the principal developer for our Sistema product. Trifona has joined Brookes Bell recently, and he comes to us with a wealth of knowledge and practical experience gained in 17 years of work in the maritime industry. As part of one of our clients' businesses, he has used our product Sistema to support shipyards in creating appropriate safe return to port designs together with the required documentation for class. And lastly, Phil. Phil has been with Brookes Bell for about 20 years as one of our developers and is our IT guru. Phil has worked on all of our software products, and today he will be providing technical support for this webinar. So if you have any technical issues that can't be resolved through the FAQ that I shared, please send Phil a private message with any issues you may have. Now, a short introduction to Brookes Bell. We're a business of circa 150 technical staff. We provide consultancy and technical support in a vast variety of subjects. I've listed a non-exhaustive list on the slide. We have many ex-seafarers in our employment, combined with some great technical staff, which can provide some really good consultancy to our clients. The software team, which is here today, is part of a business called Safety at Sea Limited, which some of you may know, and is based in Glasgow in Scotland. Safety at Sea has been part of Brookes Bell since 2013. And as Safety at Sea, we provide a number of software products to the industry. And in terms of safe return to port, apart from our technical advice to shipyards and clients, we sell two products. Sistema, which is the product you will be seeing for part of today's webinar, is a system design and assessment tool specifically designed to support designers and shipyards in obtaining compliance for their vessels. Sistema has been in the market for about 5 years now, and we estimate that about 20 cruise and ferry designs have been successfully designed and proved to class as compliant with our tool to date. Safe Return to Port on Board is our product designed for operators to support their part of the compliance for safe return to port, providing a digitized version of the restorative or containment actions for each SRTP casualty. Safe Return to Port on Board is currently installed on about 10 vessels, and we have about another 10 in the pipeline. And now, for the main part of the webinar, I shall pass on to Alistair for the presentation to begin. Once again, thank you very much for joining us today. There will be about 10 seconds of silence as we swap over. Thank you very much.
Vic. So in this part of the webinar, I'm going to go through the regulation, its intent, and the impact this actually has on the design and the operation of a safe return to port vessel. So first of all, I'm going to go through the regulation and the intent of that regulation, the casualty scenarios that are covered under it, look at some of the redundancy principles that can be employed in order to meet the safe return to port requirements, and then look at what impact this has on the design, the operation, and the life cycle of a safe return to port vessel. And then I'll briefly introduce the design example that Trifonus is going to do in Sistema after this. The regulation itself came into force in July 2010, so it's been in effect for nearly 10 years now. It's outlined in the SOLAS regulations, and it's in both the chapters about flooding and about fire integrity as well. It's applicable to passenger vessels over 120 metres in length or greater than 3 main vertical zones. However, it can apply to other types of vessels such as special purpose ships and with more than 240 persons on board, naval vessels made to ANIP 77, or yachts carrying greater than 120 persons and regulated under the Yacht Code. The main purpose of the regulation is that we require to have certain essential systems that remain operational following a damage, and those damages are either isolated fire or flood, which I'll explain in a minute, or we're looking at a case where we've lost a full main vertical zone due to a fire escalating. And we achieve this availability by ensuring that systems have sufficient redundancy, but also by an allowance for crew intervention as well. So the intent of the regulation is really this concept that the vessel is its best lifeboat. We want to try and keep passengers on the vessel for as long as possible in an emergency situation. We do this by improving the resilience of the ship's systems, and this is enforced by having to formally prove that the systems actually meet the requirements of safe return to port. And while there is an allowance that we can use crew manual actions, it's important that these manual actions are kept as minimal as possible and are as clear as possible so that the crew can respond effectively. Now, there are two actual main cases underneath safe return to port. The first one is the return to port cases where the vessel has sustained a small flood or fire and we can basically make it back to port. And there is a requirement that we can maintain 6 knots in Beaufort 8. The other side of it is the evacuation case, where we've lost a full main vertical zone and then we're just looking at supporting the evacuation process, and we need to keep the systems available for 3 hours in order to aid that process. But in both cases, the real point of this is we're trying to increase the passenger and crew safety by keeping the systems online to either safely get back to port or to safely aid the evacuation process. So the casualty thresholds, or the damages that are considered underneath the regulation, can be broke up into the safe return to port cases and then the evacuation and abandonment case. So under safe return to port, we have the flooding case, and this is just looking at a single watertight compartment. And the important thing to note here is it's just a single watertight compartment. It's not looking at multiple compartments that people might be familiar with when dealing with the damage stability regulations. The other side of it is the fire cases. And again, these are relatively limited fire scenarios. We're looking at a fire that's contained within the first set of A-class boundaries. So it starts in a space and it will spread up to the first set of A-class boundaries. However, if there's no fixed firefighting in that space, then it is assumed that the fire actually propagates up to the next set of A-class boundaries. But there's some limitations. That propagation is assumed to go outward and upward, but it will not go down to lower decks and it will not cross a main fire bulkhead. There are some exemptions to spaces which are considered for the fire scenarios. So for example, void spaces or cofferdams are assumed not to be a space of fire origin. Now, if a fire was to escalate, we then look at the loss of main vertical zone case. So this is assumed that the fire has spread and we assume that we've now lost a full main vertical zone, and we're then looking at supporting the evacuation and abandonment process at that point. A couple of key points to note about the casualty thresholds is we only consider one at a time. So we only consider a flood or a fire or a loss of main vertical zone. We don't consider a combination of the two. Having said that, obviously for a large cruise ship, this can still be a significant number of casualties that we need to consider. So, the number of flood scenarios is obviously dictated mainly by the watertight compartmentation. So we're looking at maybe 30 plus flooding scenarios for large cruise ships. Fire scenarios dictated by the A-class boundaries. So again, we're talking anything maybe 500, even up to 1,000 for a large cruise ship. And obviously the main vertical zones dictates the number of loss of main vertical zone cases. So we're talking, 5, 6, 7 for large cruise ships. So the problem is not a small one. There's a lot of different scenarios that are actually have to be considered underneath this regulation. So in terms of what's required of us in terms of the system's redundancy, so they follow a similar concept for both safe return to port and evacuation and abandonment. For safe return to port, we require that systems must remain available apart from in the affected space. So for example, if we had a fire in a compartment, it's acceptable that we have then lost the bilge suction, say, in that compartment, but it wouldn't be acceptable that we've lost it in any of the other adjacent compartments or any other compartment on the vessel, sorry. In terms of evacuation abandonment, it's a similar principle, but it's done based on main vertical zones. So we're expecting the system to be available in all main vertical zones apart from the one that's been affected. So again, if there's a fire in one main vertical zone, yes, the fire main directly in that zone may be lost, but we would expect it to be available in all other main vertical zones. For safe return to port, there's 14 essential systems need to be available. These are obviously related to systems required to help us get back to the nearest port and to keep people safely on board the vessel. And for evacuation abandonment, it's only 4 essential systems that we're concerned with, because we're obviously only looking at then supporting the evacuation abandonment process. The systems for safe return to port, grouped into kind of major groups here, are power and propulsion related systems. So that's all your power generation, propulsion systems, and all the related auxiliaries. Navigation and communication, we obviously need to be able to communicate both internally, externally, and obviously be able to safely navigate the vessel. Safety systems, so by that I'm meaning flood detection, fire detection, fire main, fixed firefighting systems, and so forth. And then we've got safe areas as well. And the safe areas is one of the key concepts of safe return to port. And these are spaces on the vessel which are marked for the supporting of passengers on board the vessel. So for a cruise ship, this could be, full main vertical zones could be considered as safe areas pretty much, because we need to keep people safely on board the vessel. We need to provide, water, sanitation services, food, and that can vary, significantly. If it's a short journey to the nearest port, then we could just be looking at using pre-packed food, bottled water. If we're talking thousands of miles to the nearest port, then we obviously need to look at actually having the potable water system online and potentially be actually supplying hot food to our passengers. In terms of evacuation abandonment, it's obviously a smaller set of systems because we're only looking at the abandonment process. So we need the communication, again, both internal and external, fire main to fight the fire that exists, the bilge system to remove the firefighting water, and obviously we need to make sure we've got the lighting and guidance systems to make sure that we can support a safe and efficient evacuation and abandonment process. So how do we achieve this? So the main way that we achieve this level of systems availability is through redundancy. And one of the main ways of doing that is through duplication. And so obviously we can do duplication at different levels. We can have duplicated engine rooms, we can have duplicated pod rooms, port and starboard propulsion, so that we can lose one and the other is still available to us. We can duplicate key equipment, things like the bilge system or the fire main system. It's common to have multiple pumps, but we maybe only require, 1 or 2 out of 3 or 4 pumps that may actually be available. Or we can look at duplicating full systems, something like a walkie-talkie system, for example. It's easy to completely duplicate that system as two independent loops. A concept which is close to duplication, and the two obviously work together, is the idea of separation. So if we have duplicated systems or duplicated components, it's important that we keep them separated in order to ensure that that redundancy stays valid. And how do we do that? So if we're looking at engine rooms, obviously we can have completely independent engine rooms. We can have no crossovers between them. This is a concept which is common in DP vessels. We can look at separation in terms of dedicated spaces, actually mark the vessel as being split into dedicated spaces for, say, the port side pod and the starboard pod. So any component, cable, pipe dedicated to one of those pods only goes through those dedicated spaces. And this means we don't get any crossover between two independent systems or our duplicated systems. Obviously, that separation is important also when we're talking about, redundant cables. It's not uncommon to have two power supplies to a single component. If that's the case, then we need to make sure that those cables remain separated from one another and they don't go through a common space. And remember, when we're thinking about those fire scenarios where the fire can assume to spread, it may not be sufficient that those cables just run through two separate rooms. They may actually need to be split, separated, either side of the vessel to ensure that they don't get impacted by the same fire casualties. And obviously, again, with duplicated systems, we want to make sure that we keep that separation. So, that walkie-talkie example, if we have two independent walkie-talkie systems, we then need to make sure that those duplicated systems are actually completely separated and there's no common points of failure. Remember, that might be points of failure as in components within that system, or it could be, common power supplies. So it's important to make sure that that separation is clear. We can look at protection, where maybe we can't get complete separation or duplication of a system. We can then obviously look at protecting the system. There's an allowance for A60 trunks, so if we have a completely enclosed A60 bounded trunk, then we can assume that the pipes and the cables inside that trunk are not affected by a fire surrounding it. We can obviously have protected pipes and cables, so piping, for example, can be protected essentially against flooding as long as there's sufficient thickness, and equally against fire as well. However, you need to think about things such as flammable liquids in a pipe. We can't assume that that is resistant to fire, and equally if it's a high viscosity liquid in that pipe, if it then went through a flooded compartment, it may no longer be available because of the fluid viscosity becoming too low. Similarly, with cables, we can obviously have fire and flood protected cables, but it's important to note that when it comes to the fire protection side of things, when we're returning to port and we've had a small fire, yes, it may be sufficient for that cable to have, an hour's worth of fire protection. However, if it needs to be available for the evacuation process, then we're talking about 3 hours worth of protection. In fact, some class societies push for 5 hours of protection if we're relying on it for the evacuation abandonment process. And obviously some equipment can also be protected in the sense that a bilge pump or a fire main pump may well operate perfectly well underwater. And manual actions, obviously, if we can't get sufficient redundancy through these measures, then we can then look at manual actions as a way of restoring systems. And really the manual actions can be broken down into 3 main types. We've got containment, so that's really kind of, damage response, damage containment. We can then look at the restoration side, is there a bypass line that can be opened up, or is there some special mode that a system can operate in safe return to port? And there may also be a need for control as well. And by that I mean, there might be a need for local control. Maybe the control system has been impacted, so the crew actually need to operate the system locally and then communicate, say, with the bridge via walkie-talkies. But the key thing about the crew manual actions is they must be minimized, both in the time it takes to complete a single action and in the total number. If you think that we have a large number of systems that we need to consider, even a couple of actions per system soon adds up to a significant number of items that the crew need to deal with in a safe return to port situation. So what does this mean in terms of design? So obviously this does have an impact on the design. And we need to start thinking about it early on, even from the operational requirements. Where's the vessel going to operate? This operational area has a big impact on, how much fuel do we need to store? How much water might we need to store? If we're far away from a port, do we need to be able to provide cooked food for passengers? Or if we're close to the nearest port, can we just deal with pre-packed food, for example? We need to look at the required availability of each of our systems. Yes, it's outlined in the safe return to port requirements what availability is expected, but what does this actually mean for each of the systems? Are there some exemptions that need to be got because it's just not possible to meet the exact requirement as outlined in the regulation? We need to look at the ship layout, with Additional redundancy, separation, duplication, it means we may need additional technical spaces, we may need additional A-class boundaries so that we can protect certain systems from one another. And obviously this ties directly into the casualty definition. And so when we look at the definition of the casualties, maybe that requires an update to the ship layout in order to make sure we're maintaining our redundancy principles, especially if we're looking at, say, dedicated spaces in the vessel. What's the design philosophy? So how are we actually going to achieve the redundancy for each of our systems? Are we going to have, full duplication? Are we going to have, duplication with some degree of separation? Or are we going to have to rely on, fire protected cables or direct manual interventions? What's the philosophy of each of these systems? We then need to assess the system. So look at that system, where it is in the vessel with our casualties, and assess it. When will it fail? Are those failures acceptable? And if they're not acceptable, that's classed as a critical failure. And in the case of a system that has a critical failure, we then need to look at doing a detailed assessment. And this is traditionally done using FMEA type approach. And this is then looking at basically, why did it fail? Are there changes we could make? Are there actions that could be done by the crew in order to restore this system? And if so, clearly outline the crew manual actions. And as I said before, the key of the manual actions is these need to be predetermined. So for each casualty, for each system, if an action needs to be done, this needs to be clearly stated as part of that assessment process. All this information will go into documentation. So all these phases need to be well documented, clearly stating the key points of each of these phases. And in particular, as I say, documenting the manual actions well. And then this needs to be backed up through testing. Now, the testing is quite often either done through harbour acceptance tests or it could be done during sea trials. And these testing generally involves picking some key cases, whether that's the loss of an engine room or whether it's identifying the case which leads to the most manual actions that need to be carried out. There needs to be some degree of testing to show that those manual actions would have the intended purpose. And that essentially means having to simulate the casualty in some way, carry out the manual actions and show that the system is restored and operational in line with the assessment. And then obviously all this information is then fed into the onboard documentation, which is really the start of the crew operational procedures for dealing with a safe return to port situation. So it's important that this information is clear as possible. So what this really means is it requires that safe return to port is considered early on in the design process. It also needs to be a multidisciplinary approach. If we've got this high level design philosophy, that information needs to be fed down to all key parties, and third-party vendors who need to know that when they're installing their system or designing their system, they need to know, oh, I've got these dedicated spaces, I've got to avoid this, I need to keep these cables separate and so forth. So it's important that everyone understands these principles. And obviously, as with all design, it leads to an iterative design. Every part of this feeds back into the previous step and therefore may require further thoughts. So what does it mean in terms of operations? So in terms of operations, obviously we now have these systems which have been marked as being the safe return to port systems, and the crew need to understand how to carry out normal operation. This may not be that different from normal operation system had it not been designed to meet safe return to port. But it is important that they understand what is the expected availability so that in the event of an incident, they understand what's an acceptable loss versus what is an acceptable loss and therefore requires crew manual actions. This can be important because the actions may not be, standard actions they would expect to have to do. And obviously some systems, especially automation systems, may even have like a dedicated safe return to port mode that the crew need to be aware of. When it comes to safe return to port response, as we've said already, there's obviously many scenarios that may need to be considered, especially for these larger vessels. There's many systems that are covered under the safe return to port requirement. And obviously what this really means is there is a requirement for crew training. The crew need to understand not only the normal operation of these systems, but they need to understand what's the general philosophy of how the system should be restored in a safe return to port incident. And then for specific casualties, what actually needs to be done. And obviously that can only be learned through continued crew training. Now, some of these points have been reflected in a bulletin that was issued by the Bahamas Maritime Authority. And this was basically outlining some of the key points. They're emphasising the need for crew training, and this should be done every 3 months. A need to minimise the number of crew actions to make for an efficient response. Be aware of time requirements. They set a time requirement suggesting that power and propulsion related systems really need to be brought online within an hour, whereas other systems, say related to safe areas and so forth, can maybe take longer to be brought online. But they is a need to consider degraded states, and by that we mean, what happens if a piece of equipment is broken or down for maintenance? What does that mean in terms of safe return to port? Is the vessel no longer compliant, or do the crew just need to be aware that there's another way that they could deal with the response? What's the impact of refits if there's been major changes to layout of the vessel? This needs to then be reflected in updated documentation. And eventually, the safe return to port process will form part of the audit. So leading on from the idea of what happens during the life cycle of a vessel. So one of the key things is what happens during maintenance. Obviously, during maintenance, equipment may be taken offline, but it may not be clear exactly what the impact is on safe return to port compliance. Is it that the vessel just is no longer compliant, or is it the crew could be made aware of alternative set of actions that could be carried out? But there's no easy way of passing this information on to the crew, and it's something that needs to be considered, and the crew need to be aware of, that they may find themselves in a situation they can't actually bring a system back online using the intended actions. Repairs, obviously, we may end up having to make temporary or permanent repairs to some parts of a system. And by doing this, it may mean that, the system is modified in some way, maybe cable or pipe runs are changed. And if that's the case, it's important to make sure that those new routings do not have an adverse effect on the safe return to port and compliance. But how easily can this information be determined? How can we determine that impact easily? And that really needs to be done using documentation that was generated at the design phase. And then taking this to the next level is obviously when we then have refit and revitalization of one of these vessels. Now this does happen. They obviously do have modifications made, and that can be, fairly major modifications to the internal layouts of the vessels, potentially some modifications to the system. And then the question is, how do we quantify those changes? If we've got a lot of paper-based documentation, how can those changes be quantified, updated, and, a new set of actions potentially generated so that the onboard documentation can be updated, and then the crew can obviously be retrained in these changes. And obviously the key thing here is we just need to make sure that the vessel remains safe return to port compliant throughout its lifetime, and that when these changes do occur, that the crew are clear what these changes mean in terms of the crew manual actions and the operations of these systems. So in summary, as we were saying, the regulation has been in effect for nearly 10 years now, but as with these things, everyone is still learning and improving the processes involved. Safe return to port covers both safe return to port and evacuation and abandonment case. In both cases, however, there is this prescribed level of availability, and it does cover most of the major systems, and it has impact both on the ship layout and obviously on the firefighting, because the firefighting availability has a direct impact on those fire casualties, which can have a very high impact on separation and therefore redundancy principles. It needs to be considered early on in the design phase, because obviously it's impacting pretty much every part of the design process, and therefore also requires a multidisciplinary approach so that all parties are involved at all stages as much as possible. It requires a formal, repeatable analysis. It's fine to do that first, full assessment at the design and delivery phase, but it's also important that analysis can be repeated, not only to take into account design changes during that initial phase, but also later on in the vessel's life. There's a need to minimize the crew actions so the response can be as efficient as possible. And it's important that everything is proved through testing, and that this is fed directly into onboard documentation so the crew have the most complete and succinct set of actions available to them. And obviously using that information is important that there's a level of crew training. They need to be trained in the systems, they need to understand what safe return to port means for their vessel, and they need to be aware that there could be impacts, say, by making repairs, temporary repairs, or taking pieces of equipment off for maintenance. And there is obviously life cycle considerations, which is feeding into that idea that obviously when more major changes are being made to the layout and the systems, these really need to be considered, and any crew documentation updated accordingly. So we're now going to go into a design example in Systema, and I'm just going to briefly introduce Systema, the user interface, and the design example before Trifonus will then lead you through it in more detail. So what is Systema? So Systema is a piece of software we designed, and it's designed to support the safe return to port design and testing process. It's based around a graphical user interface where we can design the systems, but it also has scripting capabilities so we can automate some of the more common tasks. Its key idea is it combines both the casualties and the system layouts, and the system dependencies can be modeled, which means that we're able to automatically determine the availability of the system following a particular casualty, but we can also actually automatically determine crew manual actions, so alternative configurations of the system following a casualty, which would allow us to bring that system back online. It's based around a system of automatic reporting, so the analysis that's carried out can be automatically reported, making it very easy to make changes within the model, rerun the calculations, and then automatically update the reports. This means that we've got full life cycle support, so we can support that initial design process, but it also means when the vessel's then in operation and changes are made, these can be reflected in the systems model, the calculation repeated, and the documentation updated. And we can also look at beyond safe return to port. Safe return to port also only looks at these limited fire and flood scenarios, but with Systema it's possible to look at combinations of the two, look at multi-compartment flooding. Yes, not required by the safe return to port requirement. However, it can be useful information to the operator to understand, what systems they should be expecting to be available in different, casualty scenarios. So example we're going to go through, I'm going to briefly just give you highlights of the Systema UI to make the example a bit clearer for you. Trifonus is then going to take you through a freshwater cooling system. This is going to highlight some of the issues with a sort of, just a system that's been designed without safe return to port being considered, and then look at how we can modify that design and then eventually making the system fully compliant with the safe return to port requirements. Systema itself, so this is the main user interface of Systema. On the left-hand side, you can see we've got our representation of our ship model. We've got a profile view and a deck view, and this is where we interact with the ship model side of things. And then on the right-hand side, we have the diagram view, and this is where we actually build the system itself. As I said, the model that we're building up is location aware, so every component, every cable, every pipe has a location within the vessel, and that's obviously how we can then apply a casualty to that particular system or systems. The systems are functional, so by that we mean that every component actually has a series of inputs and outputs, and the outputs of a component are dependent on its inputs, which can be defined within the software using Boolean logic. The systems are connected, so by that we mean that the output of one component is connected to the input of another. So if that output was to fail, then the input of that component fails, and therefore we can have that knock-on effect of a functional loss. And those connections between components could be within one single system, or we can have connections between subsystems. This means that our model is fully connected, and therefore the failure in any given system, the impact of that can be determined on all the other systems in the model. In terms of viewing results, I say we've got the automatic reporting, but we don't have time to kind of go through that today, and it's not of much interest for the example we're showing. But what we will see is we'll be showing you some of the diagrams with the highlighting on them. And the highlighting in this diagram here is just showing us the impact on a system following a casualty. So the highlighting basically shows us where we have green, that's showing us items which are not physically damaged and are still fully operational. Red is showing us where we've got physical damage. So this is a component or a connection that has been directly impacted by the casualty. We can have orange damage, not shown in this particular diagram, but that is basically propagation of damage. So for example, depressurization of a pipe. It may not be actually in the physically damaged location, but because of a failure further upstream, it means that we get a depressurization along the full length of the pipeline. Yellow is showing us unrestorable functional loss. So by that we mean components or connections which are not actually physically damaged, but because of the failure of a component in terms of producing an output, it's no longer functionally available to us. And then we have the blue highlighting, which is basically showing us where we've had a functional loss, but it is restorable, as in there are crew manual actions available to us, which allow us to bring that part of the system back online. And you'll see that on this diagram, you can also have a combination of the highlightings, and that's basically where we've got two directional flow. So one way, maybe it's unrestorable, but in the other way, other direction, sorry, it is restorable. We can also look in detail at individual components we wanted to. So for example, here we selected one of the pumps, and we can then see that the inputs and outputs are actually highlighted in a similar manner to let us have some upfront information. And this can be very useful to look at individual cases in detail to understand what losses have occurred and why. So I'll now pass you over to Tryphonis, who's going to go through the example.
Thanks, Ali. What you are seeing on screen is an example of a freshwater cooling system in our software Systema. I'm going to take you through the steps required in order for this design to gain safe return to port compliance. A freshwater cooling system shall comply with the fire and flooding casualties according to SOLAS requirements. The system design was based on work done in similar projects developed in a redundant way at higher level, but as we'll see later on, critical failures have been identified. By the term redundancy, we mean that there are two independent freshwater circulating circuits located at two different spaces, one in the forward engine room and a second one in the aft engine room. Each circuit is equipped with two heat exchangers, one in operation and the other standby, two circulating pumps, one running and the other standby. The pumps in each machinery space are powered from two electrical cabinets for redundancy, and they are controlled by the automation control system on board. Each circuit is cooling a propulsion unit comprising of the pod unit and its associated drive, two diesel generators, an air conditioning unit located in main switchboard room. Each engine room has its own switchboard room. Also, each circuit is connected to the freshwater cool stabilizers in the stabilizer room and air compressors in the service aggregator room. The design intent or philosophy of the freshwater cooling system is to maintain the flow to the relevant safe return to port consumers, such as diesel generators and propulsion units, under any fire or flooding casualty. The pipes and the cables, represented by green solid and dashed lines, are routed not to cross the same spaces as possible. The supply line of each propulsion unit is routed differently than the other. This is the pipe route to the port side propulsion unit, whereas this is the supply line to the starboard unit. However, due to pressure losses and few other technical concerns, the return lines cannot follow the same routing pattern as the supply lines. Therefore, they are crossing common spaces. As far as the stabilizer unit concerned, both return and supply lines are routed through common rooms. This is for the Unit 1 supply line and its return, and this is for the stabilizer Unit 2 supply and its return. The common space where the routing is taking place is the forward engine room. For the air compressors located in the service aggregator room, the supply and the return follow different paths. This is the supply of the air compressor unit 1 and its return, and for the compressor unit 2, this is the supply line together with its return. By running the Systema model, we have identified 4 critical fire scenarios and 6 for flooding. The 4 critical thresholds for fire are related to the following spaces: aft engine room, forward engine room, stabilizer room, service aggregate air compressor room. The spaces as measured for fire, plus 2 extra ones, 2 void spaces at the aft back of the ship, void 1 and void 2, are critical for flooding. When the service aggregate room is lost due to fire or flooding, all the components in this compartment are physically damaged. These are highlighted in red. All yellow highlighted components, such as stabilizers, heat exchangers, pumps, diesel generators, and the propulsion units, have lost their functionality and cannot be restored. The orange pipeline is depressurized. This is due to red highlighted damaged pipe. Components, shown in green, like the motor control center and control cabinets, together with their associated cabling, are intact, with no effect on their functionality. When the stabilizer room is lost due to fire or flooding, all the components contained therein, including valves and the stabilizer units, are physically damaged. This situation is similar to the loss of the service aggregator compartment. In addition, pipework will be depressurized, components such as pumps, diesel generators, and the propulsion units will lose their functionality and cannot be restored. Items like MCCs, control cabinets, and cabling will remain intact. Another one critical scenario is the loss of the forward engine room due to fire or flooding. The functionality of the propulsion components, as highlighted in yellow, together with those in the aft engine room, such as diesel generators, air conditioning unit, pumps, and heat exchangers, is lost and cannot be restored. This is a similar outcome to the loss of the aft engine room, stabilizer room, or the service air compressor compartment. To comply with the safe return to port design philosophy, maintaining one circulating circuit operable, either in the forward engine room or in the aft engine room, together with one propulsion unit from port side or starboard side, the failure should be contained. This is done by installing isolating valves in to the supply and return lines from and to each engine room. By selecting the space in deck view where we like to add a component, Systema gives us the option to choose the type of that component, edit its detailed location and description. Also, from the diagram symbol drop-down menu, we can choose the appropriate symbol for that component. By clicking OK, we can select that component and we can place it on the system diagram. By adding isolating valves to supply and return lines of each circulating circuit, the pipework depressurization caused by damaged components or pipes in different casualty thresholds will be no longer an issue. The damage containment valves shown in the dashed blue boxes at the aft engine room, at the supply line, the return line, similar, supply, and return, and at the aft engine room, containment valves at the supply, the return, supply line, and the return are manually operated. The system can incorporate any type of valves, manual or automatic. In case of automatic control valves, their arrangement, including power supplies and control, should be compliant to safe return to port requirements and allow manual operation. To cope with the return line damage from the starboard pod room due to flooding of the void space 2 or void space 1 or the aft engine room, the pipes should be protected against hydrostatic pressure. The same can apply to the return line of the port side pod room. This line crosses the same spaces as the starboard pod room return line. Using Systema features to adjust vulnerability of pipes components by untick the flood damage case. And similar to the port side pod room return line, we will untick the failure damage case and then press OK. In reality, most of the metallic pipes and their fittings can sustain external pressures up to 1 bar or even higher. By introducing these changes in the Systema model, the software will calculate and identify the containment manual actions required for each scenario, as we'll see next. For the air compressor compartment loss due to fire or flooding, Systema has identified the loss of the component's functions together with their connectivities. Also, it has calculated the required manual actions to contain the failure. The damaged components and their associated pipework are highlighted in red. The yellow valves in the aft and forward engine rooms related to the air compressor's cooling have lost their functionality, meaning no flow in and no flow out from that component. This is caused by closing these valves to prevent the pressurization of the freshwater circuits. The remaining parts of the circuits, as shown in green color, are intact, including the cooling provisions of the propulsion units. These solutions satisfy the design intent of the safe return to port philosophy. We should mention at this point that loss of air compressor is acceptable. For the stabilizer room loss due to fire or flooding, Systema identifies the loss of functionalities and calculates which valves have to close to contain the damage and prevent circuit depressurization. Due to pipe routing patterns, 2 additional isolating valves in the aft engine room will close. This will result in loss of air compressor's functionality as highlighted in yellow. To avoid that, both supply and return lines of compressor unit 1 should be designed to withstand the impact of the hydrostatic pressure similar to the pod unit return lines. This scenario represents the loss of void space 2 due to flooding. The port side pod unit's return line has lost its functionality and cannot be restored. This is due to the physical damage of the supply line. This is easily fixed by making this line not vulnerable to flooding, a technique we discussed previously. The loss of the starboard pod unit's electrical control room will result in the damage of the I/O racks essential for pump control and operation. Subsequently, the functionality of the standby pump in the aft engine room, together with that of the running circulating pump in the forward engine room, is lost. This failure is not critical because there are 2 remaining pumps controlled by I/O racks placed in alternative locations for redundancy. If required, the affected pumps can be reinstated and operated locally. The aft engine room loss due to fire is critical damage. The supply and return lines of the port side propulsion unit, together with the return line of the starboard propulsion unit, are damaged. This results to the loss of 2 propulsion units' functionality. This is not acceptable according to the safe return to port design criteria. Therefore, a design modification is required to maintain the cooling circulation in the starboard propulsion unit under any casualty threshold. Adding an extra dry line of sufficient thickness and 2 isolating valves between the starboard pod unit and the forward engine room is an option that we will discuss next. Having assessed the Systema's results from different casualty thresholds, few modifications are introduced in the system model. Most of them were previously discussed. These are summarized as follows: protecting the supply and return lines of the compressor cooling networks against flooding, protecting also the supply line to the port side propulsion unit against flooding, installing a pipe of adequate thickness complement to the regulatory body's requirements and 2 extra manual operated valves, we will call these components SRTP line and SRTP valves respectively. When the aft engine room is on fire, the functionality of this line can be restored by opening the two normal cross valves. One is installed in starboard pod unit room, whereas the second one in the forward engine room. One scenario has not been previously mentioned was the loss of decks 4 and 5 due to flooding. These two decks belong to the same watertight compartment. This is the area where the supply line of the starboard propulsion unit is routed. By protecting this line against flooding, we preserve the flow, therefore no impact to the connection functionality, plus the valve located in the forward engine room remains open, reducing the amount of manual actions. For the stabilizer room loss due to flooding, Systema has calculated the containment actions after applying the modifications. The two valves in the aft engine room, together with the other two valves in the forward engine room, highlighted in yellow, have to close to prevent the pressurization of the circuit due to stabilizer unit's damage. Therefore, the functionality is not restorable. It appears that both air compressors in the service aggregate room, highlighted in green, and 4 valves in green, 2 in the aft engine room and 2 in the forward engine room, remain functional, reducing the number of the manual actions. A non-critical failure that caused the loss of port side propulsion unit was the damage of void space 2 due to flooding. The flooded compartment depressurized the supply line, and subsequently the functionality of the pod system was lost. Components highlighted in yellow. As a result, 2 isolating valves had to close to contain the damage. By upgrading the line to sustain the flooding, Systema has recalculated the containment actions. It appears that no actions are required after the modification. Both valves in green are open and functional, with the propulsion unit fully operable. All components of the propulsion unit highlighted in green, and beneficial design change with positive impact to vessel operation. During normal operation, the two SRTP valves together with SRTP line are not in use. When the aft engine room is on fire, the main return line, highlighted in red, is damaged due to the pressurization. To contain the damage, the yellow highlighted valves have to close. The SRTP valves end line in blue have lost their functionality, but it can be fully restored. This is done by opening the valves manually, allowing the water to flow in the pipe. The SRTP pipe is not vulnerable to fire. In summary, by using the software, we check the behavior of the freshwater cooling system under different casualty scenarios. Having assessed the generated Systema results, we introduce appropriate changes by installing isolating valves in aft engine room and in the forward engine room. We protected supply and return pipes against flooding and added a SRTP line together with SRTP valves. This improved the system functionality and made it fully compliant to safe return to port design requirements. Also, it helped us to optimize the number of manual actions. And now I'm passing it back to Vic.
Thank you very much, Trifonas. Now, if you give me a few seconds to get control and start the Q&A session. We've got some interesting questions, and if you give me a second, they will come on the screen. Right, our first question. Restoration should not include actions related to containment. Is it correct? I'm going to pass that to Ali to answer.
So I think this particular question maybe comes down to a distinction between the initial damage response and the safe return to port response. So obviously, if there's a casualty on board, you can't move into the safe return to port mode unless you know it's a safe return to port condition that you're in. So I think it's accepted in operators, at least the ones we've talked to, that there would definitely be your standard, damage response in terms of determining what the damage is and then carrying out your initial sort of damage containment. So yeah, there'll always be damage containment, in the sense of if you've got flooding, then yes, you will do your normal procedures, to try and isolate that particular compartment that's flooded. And that may include containment in the sense of, closing valves and things to avoid any cross flooding between two compartments. However, when we're talking about containment in terms of when we were describing it in the presentation and in the software, we were meaning, anything where you're isolating part of a system. So, there might be the need to isolate part of a system as part of your safe return to port response, which wouldn't have been considered as part of that initial, damage response or damage containment. Maybe you need to, isolate one particular line so that you can then use a bypass line, for example. That probably wouldn't have been considered as part of your damage response, but it would be required in order to actually bring the system back online. So yeah, there's definitely some maybe crossover between this idea of containment and then restoration actions. So I think in response to the actual question, then no, I guess that's not technically true. I think you could say that there are some containments required as part of the system restoration.
Thank you very much. On to the next question. I haven't understood what happens if a part of a system is offline for maintenance, such as 4 gensets on board divided in 2 engine rooms, 1 genset offline for maintenance. Am I still SRTP compliant? I'll pass this on to Trifona to answer.
Yes, hello. This is a good question. What's my point on that? That there should be an awareness of impact of having one component offline. For example, for diesel generators, especially for diesel electric ships, it's more important than having a pump. Normally, pumps, there might be one running and one standby. So if you lose one, you have the other one. But in the case that you have 2 engine rooms containing 2 diesel generators, and you lose one engine room, and in the other engine room, the other one of the engines are in maintenance, probably this might have, an impact on the performance of the boat during the safe return to port journey, which is 6 knots under 8 buffer. So yes, it's important that there should be an awareness about that.
Thank you, Trifona. And the next question, what kind of inputs from ship designer are required to engage system analysis? Only PNIDs or composite layouts as well? Trifona, if you could answer this one as well, please.
Yes. Normally, the safe return to port assessment requires a set of information. For example, we need the design intent for each system to comply with safe return to port. We need definitely the general arrangement plan, engine room arrangements, tank plans, watertight integrity plan, structural fire protection, very important. Something that I consider especially important is the arrangement of A and B grouping, which indicates and includes the segregation of propulsion and power generation into A and B groups, the redundancy. And it would be very useful also if there is any preliminary or any ideas about, or thoughts about the basic routing, cable routing for main components like the main switchboards or components like fire or bilge pumps. And also, last but not least, sorry about that, an LSA plan life safety plan, which is important for the safety centers.
Thank you very much, Trifona. So we've got another couple of questions that I haven't got in my presentation here that I will answer. So firstly, what typically is an acceptable number of crew manual actions? Now, there is no such specific number in the regulations, and the people to answer that question really are class. The main thing to point out here is that there are requirements for the actions to be able to be completed in 1 hour. If you look at the Bahamas Instruction Notice 179, they give some more extra detail about that, splitting systems into Category 1 and Category 2, and asking for all Category 1, which is basically power and propulsion, to be done within an hour, and all Category 2, which is basically most systems to do with safe zones, to be done within 2 hours. A few last minute questions. It was mentioned in the beginning that Sistema was for SRTP scenario. What about evacuation, orderly evacuation and abandonment? Can that be simulated in the system? So Sistema is a system design and assessment tool, and so it does not perform evacuation. However, we do actually offer a tool called EVI, which allows you to look at simulations for evacuations and provide assessments to class. So there are a few more questions, if you give me a second. So since Sistema designs the systems and the needed actions in the event of damage, can Sistema information be fed into a power management system or damage control system to automatically take actions to close safeguard systems? So there is no such connection at the moment. Sistema can certainly give you the correct restorative actions, and those could be used, but some integration would need to be done in that side. There's a last question. Can Sistema be used to design simulation scenarios for crew training? In that sense, yes, in the sense that Sistema can be used to create the actions and can be used to, the information from Sistema can be used to create the test plan to prove compliance to class. So I think that will be the end of the Q&A sessions. Hopefully we have captured all the questions that have come. Just to finish the webinar, we have created some resources available to download for those of you who are interested. If you follow the link that Phil has just posted into the chat, that goes to our website, and under there we have a couple of PDFs for you to download, an SRTP essential systems list, and also a further reading list on the subject of safe return to port. We also have created a short prescribed Sistema example where you can, it will take about 5 minutes, and you can basically simulate what Trifonus just showed you and get a feeling for the Sistema software. Just as we finish the webinar, we do have further webinars that we are planning. We have one that is on the operator's perspective of safe return to port, very much looking at the regulatory requirements from an operator's perspective, and we will also be showing you our tool SRTP on board. We also, and there was a question obviously on evacuation, we will be doing a webinar on evacuation analysis and the new regulations that have come into place in 2020, and we will be showing our EVI tool. If interested in attending, please send an email to sistema@brookesbell.com or connect with me on LinkedIn. Alternatively, if you've selected yes when you registered in allowing us to send you an email, we will send emails to tell you about dates about these webinars. Also, please use that email address if you have any questions post the webinar. So at this stage, thank you very much for coming, and I hope this has been informative and interesting. And please do get in touch for any further questions. With that, I'm glad to close the webinar. Thank you very much.